All right, so thanks everybody, and today I'm going to speak about this joint effort between three universities, effectively, University of Illinois, Waterloo, and Kansas, potentially a fourth one, but we'll see. And let's get started. Sorry, excuse me in advance if I'm going to be a little bit fast over some concepts that I probably are already in the public domain. All right, so, well, this is a little bit of a story, right? What happened with multi-cores and why we care. Well, roughly in 2006, they became mainstream and they invaded the embedded domain. And by now, we may think that, we see the application in the industry, and we think the industry knows exactly how to deal with it. But today, a lot of talks were exactly on the opposite side, saying, well, we don't know anything about it. And in fact, until 2016, roughly, FAA never spoke even about any guidance about these systems, multi-core systems, safety-critical systems on multi-core platform. And in fact, the latest thing that we have is a guidance, CAS 32A, that we'll quickly review today, the main points, that effectively suggests some strategies, very high-level strategies on how to try to certify multi-core systems for avionics. At the same time, we have that effectively, as of 2017, there is no standard. Just some guidance, some ideas. And at the same time, well, software is becoming increasingly more complex, from fighter jets to cars. They're probably the most complex systems in large scale. Now, the reason why multi-core are challenging, well, we address several of those issues. Well, we talk about some of those issues today, and range from problem of achieving predictability to porting, understanding a new platform, as well as follow certification that probably is not even there. Actually, not even there, at least in terms of a standard certification. But today, SCE tries to address the problem of predictability, and predictability is a problem on multi-core because, well, you may think that execution flows happen in parallel, but in fact, as again many people already stressed, there is a whole shared pool of memory resources. Effectively, the memory hierarchy and I/O as well is being shared and represent an inherent point of serialization between the executing flows. And now, effectively, what we're saying is that if you look at this as a migration problem, we are going from depending on the terminology, but what we could call as a federated architecture, where each system, each sphere of concern was a node, consolidated on a node, to a system where, well, these nodes are migrated into cores. And now the cores are not anymore connected with the nice and nicely analyzable real-time network underneath, but rather they share resources, and they share in a way that this sharing is designed in a way that it has no concern for real-time guarantees. It does not provide real-time guarantees, and actually it's trying to optimize different metrics, throughput, average performances, and actually ends up harming real-time guarantees, harming in a sense that the pessimism of an analysis there is inherently high. And so because we have this architecture, we have to plan ahead. But first, let's see how bad it is. Why it's a particularly bad architecture if we don't do anything, do any management. So we designed this benchmark. It's actually we roughly designed, and then engineers from Lockheed Martin were kind enough to run it for us and collect some details on their own setup, their own system. And what we saw is that, well, the setup is as follows. We have one synthetic task that we observed, called it application A. And this application A is normalized and the execution time is 1. And this is the case when application A is running alone in the system. There's only one core active, the core of application A. And then we start deploying interfering tasks, but they are not interfering from a logical point of view. There's no serialization, synchronization between these two applications, or these end applications. They are just running separately on different cores and occupying or utilizing or contending on the shared memory hierarchy. And now, as we turn on more and more cores, effectively the runtime of the originally observed application A, we call it, increases linearly until hitting this point right here, which is roughly 6x. Okay, and then it's not deterministic, so if we increase one more core in terms of activity, it actually goes down.
Actually, I want to make a simple amendment. We give them the synthetics, and then they said, we copy something bad. They want to try the real thing.
Correct.
The 7 is 600%. It's not from our synthetic. It's from the actual application at well cooling and worse than our synthetic.
I see. Okay. Well, thanks for the remark. That's a good point. And so what we told them is, well, why don't you deploy some of our techniques, a subset? And I'm not going to give the details because the details are my talk. And so what we said was, well, deploy some of these. In this case, they're actually just managing the shared cache. And it turns out that if you do that, the interference that you observe is much more controllable. It's not zero yet, right? Because you still have several tasks sharing resources, but it's manageable, going to roughly 50% increase, like 0.5x increase compared to the 6x. And now, looking at, before entering the details, where we are in terms of guidance, right? And then we will see how what we are doing sort of maps to the current philosophy of the database. So this is CAS 32A, and you know there are a lot of very good points in this document, but I'm going to highlight a few of them that I think are very relevant. Well, for the first time, we see the concept of robust partitioning, which is a combination of actually two things. Well, it's actually start with MCP platform, multi-core processor platform with robust partitioning. That boils down to two things. Resource partitioning, which is typically known as somehow spatial isolation, and robust time partitioning, which is temporal isolation. Now, if you look at the definition of this, it's saying, well, that no partition consumes more than its allocated execution time, no matter what, effectively, no matter what's going on in the other cores. That means that either you are very pessimistic or you bound the contention, and then you can come out with bounds that are a little bit tighter, but no matter what's going on the other core, effectively, no matter where the other partitions are active or not. And that's very important. Now, what are the other points? Well, it's telling you, I'm going to report here the headings that I'm referring to into the documents. Unfortunately, for space limitation, I have to compress them a little, but they're effectively one-to-one matching. It says, well, when you plan the software, you have to plan in a way that you have a good idea on how to mitigate the contention, the shared resources that is going to be there. And the second point is, well, when you then later on start start applying this plan somehow, you have to be sure that you are identifying all the major, at the very least, sources of interference. So these are the things that can go wrong, effectively. Moreover, it's telling you, once you identified the sources of interference, and you know that your partition has access to certain resources, then you have to make sure you don't saturate those resources. So you use the resources below the saturation limit, if you want. Don't exceed the capacity of those resources. And then it's telling you, well, now, if you have done things in a certain way, and you achieve this magic robust partitioning, which we said is a combination of a time and space partitioning, then there is a chance that I will let you certify this thing by looking separately at the behavior of the different partitions on the different cores. There's a chance, right? There's also a case for when you don't have robust partitioning, which pretty much says, well, then you gotta come out with a good plan and show me you can do it even if you don't have a nice isolation. But I believe this is the sort of the preferred path, implicitly speaking, in the guidance. And now let's look at SCE, how single core equivalence does things, and then we'll go back and see the mapping between the guidance and how SCE is designed by principle, not the implementation itself. But basically, we take a multi-core, cache-based multi-core, and let's not talk about the I/O, but look at what we identified. Remember, identification is an important part of the guidance. How we identified the resources that can create a problem, and these are roughly highlighted in red. We just determine the interconnect at this stage, at least, is not a big issue. And for each of these resources, effectively, we design a technique that exports a logical view of the resource, which is a per core view rather than a conflicting interfering channel. And so for the cache, we use color lockdown, and we do a similar thing for the DRAM. We use Palo, and then for the memory controller, Ichigo is right here. He's the inventor of this, which is effectively a way to divide the available DRAM bandwidth. And now, without giving further details, because we will try to explore a little bit them in detail, but the idea is that look at the resulting architecture. This is effectively an architecture where the concern about the timing is divided on a per core basis. You can try to analyze that in on a per core partition, if you want, timing partition base. And now all this constitute what we call SCE, which is a framework of OS level techniques that try to go from a traditional multi-core architecture which is cache-based, which has shared resources, to a view of it which is partitioned per core. And so we went in and we implemented this on the P4080, which is a platform that has been coming over and over again during the presentations today, and it has a bunch of desirable features. That's why it fits very well our approaches.
We should mention, I just recommend like Greg.
Correct. Yes. But it's Greg definitely was one of the first inputs that we had on selecting this platform, and then confirmed.
Documents we couldn't get. So
yep.
Thank you.
Yeah, that's true. And also this interest was confirmed by the engineers at Lockheed. They also wanted to experiment on this platform, and probably now we are transitioning toward the new generation, which is a glorified P48. It's going to be very interesting to see what we can get there. And so, effectively, the first technique is color lockdown. I'm pretty sure some of you have heard about it, but basically, what allows you to do is address all the sources of interference. Typically, we classify the sources of interference of the shared cache. We're talking about the shared cache here. What we have is, intercore interference. What's the historically has represented the most worrisome part of the cache of the memory hierarchy, but also you have interference on the core itself. You have self-eviction, and you have self-eviction within task evicting its own area of memory, its own lines of cache, and you also have intra-task on the same core evicting each other at preemption point. Those can be analyzed, but core lockdown effectively gives you a way of working around that sometimes complicated analysis. Remember, we want government agencies to be able to handle certification. And so addresses all the sources of interference, and also converts effectively the cache in something which is purely deterministic. It's not anymore, has nothing to do anymore with the cache replacement policy. We effectively override this policy altogether. And basically, it doesn't touch your application. Works at the virtual to physical translation level, and effectively doesn't really affect the developer, as long as the operating system has support for virtual memory. And then the nice property is that provides full flexibility of allocation. So we're not tied to partitions anymore. We are really tied at the granularity of a page. You can decide where a page goes. As long as there is space in cache, you can allocate it. It doesn't matter if one core takes 99% of the cache and the other core share the remaining 1%. You can still have that granularity at the level of a cache page, effectively, for KT. Now, what is important to remember is that, unlike partitioning, we have to decide explicitly what goes in cache. And this is, in my opinion, the biggest advantage, in the sense that partitioning in the end can be more harmful than beneficial if you don't have a clear idea of how the task is using the partition. In the sense that it's very easy to have a task that behaves bad in a contention case, and when you create a partition where you confine, you reduce the contention, but because you reduce the size of the cache, the task behaves even worse. In this case, instead, we follow a different approach. We first decide what goes into the cache, and then we decide where the content that you want to allocate is supposed to be locked in cache, and finally we perform this allocation. A nice property that we have that would simplify the certification step is this property, which means whatever you allocated, it will result in 100% hit rate, and whatever is not allocated will result in 100% miss rate. So now the hit-miss classification at analysis level is trivial, because you know exactly what's going to hit and what's going to miss. There's no ambiguity there. the way it works a little bit at the lower level, but I won't go further than this. Effectively, it's a combination of two techniques. Coloring, which is used to move pages up and down, and as I said before, it uses the virtual to physical translation to manipulate where the cache line, or the cache page in this case, maps in our physical cache. And somebody talked about this today, so I'm assuming that you're confident about how this works. And then we said before, well, it allows the use of legacy codes. Effectively, it's transparent to the designer and the application, and finally allows you to have full control of this dimension. The other dimension instead is handled through lockdown. Lockdown allows this horizontal placement of pages in cache. And of course, in order to perform lockdown, we have to rely on support that is provided by the architecture, but we saw that it's pretty consistent in those architectures that are intended for safety critical domain to provide this kind of support in different ways, in different declinations, but it's pretty common. And especially in PowerPC, because those are the platforms that are more friendly to avionics or safety critical in general, including automotive. And the interesting thing is that's where the deterministic property comes into play, is that once allocated, a page will stay in cache until further reallocation. And so this solves the cache, but we have still one problem. What do we put in cache? And effectively the problem can be rephrased in, well, we have an application with a certain address space. And we know that something is more important than other pages to be allocated in cache, right? We have to be very careful here. Otherwise, we lose the benefit of the cache itself. So what we do in order to spot which pages are important, we run a profiler. We sandbox our task, and we collect a trace. This is what we do right now. And then we create this application profile, which is an application global profile, where we say, well, this page has been accessed this many times, this other page has been accessed this many times, and so on and so forth. And we create this nice table. And now we can do fun things. For example, we set a threshold and say, well, whatever is above the threshold goes in cache, is allocated, because I know it's important for the timing of the application. And whatever is not important, or rather less important compared to other tasks, is will result in a miss. So it's going to translate into DRAM memory access. And we collect this into a parameter we call mu. And we'll come over and over again, so remember this mu is right there. And I want to attract your attention on something else. Well, when we decide the threshold, right, we are actually defining one more relationship between how much cache you're using, or if you want on this axis right here, and the timing that it takes, so the benefit that the application derives of having that part of its own memory locked in cache. And so whenever we choose a point here, we have two pieces of information. The mu, that we already discussed, is the number of misses that will be directed, well, number of memory requests will be directed to the DRAM subsystem at runtime, aka misses, and the time that it takes to perform its execution. Notice that right now, we didn't talk about contention. In fact, all this analysis is done in isolation. And this is very important, because we are saying, now you can apply whatever procedure you had before to try to derive this number, WCT1, in isolation. In isolation means when all the other cores are turned off. So this is the worst case execution time with a certain cache assignment, but when only one core is active, which is the core where you're running your task under analysis. And now, remember these two parts, WCT1 and mu. Now that we solved the cache, let's get the cache out of the picture and look at whatever is left, right? This is the DRAM subsystem, memory controller and DRAM storage. And if you expand the DRAM, you realize that, well, it's actually structured in different banks that can operate in parallel. But the problem is that the operating system, as somebody pointed out in the morning, well, typically doesn't know where physical pages are mapped. So what happens is this average case scenario, where every core can access any bank, right? But there's one case which is even worse than this, which is the case depicted in this figure, meaning that all the cores are now serializing on the same bank. That is the worst case, because you have the worst case interference, but also the worst case behavior of your DRAM storage. And now, if you expand the other part of this figure, which is what happened in the memory controller, what you have is, well, you have a bus, right? That typically is arbitrated in a round-robin fashion, but after that you have an arbiter. And the arbiter effectively translates memory requests into DRAM bank commands. And now, once the translation is done, typically, and it depends on the architecture, but typically the command goes in a per bank queue. So each bank is independent from each other, as I said before. And you may think that this is the end of our problems, because these are technically conflicted, right? Parallel resources, but in practice is not the case. Because if you zoom on one of these, what you can see is that you don't have the nice FIFO ordering in this queue, but you have something evil called first ready, first come, first serve. And first ready, first come, first serve effectively reorders what's in the queue, meaning that your application can be ordered after a bunch of requests coming from other cores. And that's why you suffer interference. And now, let's step up a little bit and say, let's look back at the OS. The OS has a problem, which is it doesn't know the mapping between physical and bank addresses. And effectively with Pavlov, what we did was a little bit exporting this knowledge of how the underlying structure of the banks is organized to the OS level, so that we can enforce this, what we call private banking policy, where each core is assigned a non-overlapping set of DRAM banks. So now each core accesses different banks. This is the solution that was described in the morning in Q plus A from April. And now, because we do this, well, we prevent request reordering effectively. There was a nasty feature of the DRAM policy. And we also do something else that I won't detail, but effectively it's something that benefits your application, but at the moment we're not really able to capture in our analysis. So let's keep that for now. So now one more slide that I want to show you about the next problem, which is, well, we say how we can deconflict the banks, but we never talk about what we do about the memory controller. Remember, there's an arbiter there. And the arbiter is a shared resource. And the arbiter can get congested. And when the arbiter is congested, you can't really see or analyze a round robin anymore. It becomes something more complicated. So what we do is, well, we consider the total DRAM bandwidth that is being extracted from the DRAM subsystem. And now we put two bars effectively. There is something we call BW mean, guaranteed bandwidth. And the idea is that if collectively the cores are behaving in a way that stay below this threshold, we know for a fact, we can derive it from the documentation, that the arbiter is not saturated. So we can nicely analyze the behavior of our core. So if you want, each core is receiving a fair share of their bandwidth. But if we go above this threshold, and the problem is that we cannot know whether or not we are above or not by only looking at the count of requests, so that's why we have to be conservative. Everything may be fine, right? But there are cases in which the cores are extracting an unfair amount of bandwidth from the DRAM subsystem. And for this reason, we designed, well, actually, is original Ichul's work, we designed memguard, which is a way to regulate the behavior of the cores so that overall they don't exceed the BW mean, global quota. And so now we have effectively cores that have a memguard regulator attached to each of them, and each of them has an equal amount of budget in terms of memory transaction they can perform, and the global has to be less or equal to the BW mean. That's the intuition behind it. So that the arbiter is not saturated and we can run an efficient analysis. So if we now put the pieces of the puzzle together, we have core lockdown, and we derive WCT1 and mu. And then we have padlock that avoids some nasty effects in the DRAM storage. And also we have memguard, as I said, that prevents arbiter saturation by doing this fair, in this case, fair bandwidth partitioning. And because we have all this together, we were able to derive something we call WCTM. What is WCTM? It's the worst case execution time of the task under analysis, but when M cores are active, and regardless of what the other cores are actually doing. In fact, we can derive this. This is a little bit of lengthy derivation, but it's a very simple formula that basically takes into account WCT1 and then is inflated by some amount that depends on the number of transactions. Actually depends on the total DRAM traffic, with L size the line size, so the granularity of the transfer from the DRAM banks. And as a factor is effectively multiplied by the BW mean divided by a factor of m, because now remember that the quotas are all equal. So it's the available bandwidth, guaranteed bandwidth is divided into equal parts, divided into m parts. And now a little bit of a summary here. What we did was, well, SCE is this framework of OS level techniques that enforces partitioning, temporal partitioning, and it's composed of well-color lockdown for the shared level of cache, composed of padlock for the DRAM, and memguard for the DRAM bandwidth, so the memory controller bandwidth. And on top of that, we were able, because we have these nice guarantees, we were actually able to derive this analysis. As I mentioned before, it's for equal budget reservation, but now it's going to be out in the summer. We're going to present it in Dubrovnik in ECRTS, a new analysis that actually allows you to generalize this system and calculate WCT, not M, but Q, because Q is the vector of explicit budget assignments, when you can assign different quotas. Imagine you have a high-performance cluster and a low-performance cluster, and you want to differentiate the budget assignment between groups of cores. So what I want to go back is to this slide. That if you remember that, we saw the main points of CAS32. And now, just to recall them, I put them back on the screen. And I want to see the mapping, sort of, with the approach of SCE. Not the technology, not the implementation, but just the philosophy behind SCE. Well, the first thing was we want to achieve robust partitioning, because that we know is going to be a combination of two things, right? It's going to be a temporal and space partitioning. Well, guess what? This is exactly the goal of SCE. SCE is targeting a strong intercore isolation from a timing perspective. And well, it says you got to plan how you're going to avoid and mitigate the contention. Well, guess what? The whole point of SCE is provide you a plan how now to deconflict all the major sources of interference, not all of them. Somebody was talking about the TLB today. Well, those have to be incorporated, but at least we're trying to address what are the elephants in the spectrum of problems. And for research usage 3, well, in the SCE workflow, what we embed is methods to identify what are the sources of interference coming on your multi-core system. If you take the academia version of SCE, some of the study has been already done, but for a new platform, for a new architecture, well, that study has to be performed yet, but we have tools to address that problem. We have at least know-how on how to do the new analysis and find out what are the sources of interference in new platform. In fact, we have a whole chunk of work on automotive where the first step was exactly we're using some of this know-how. Yeah, and so in the end, the goal is effectively, once you've done this step, to operate, to make sure that the timing is guaranteed, we have to operate the resources below the saturation point. And this is again embedded in the way SCE is designed. In the end, by doing all this, we get that our system is going to export robust temporal partitioning, which in the end is an important component of robust partitioning, which in the end is the ultimate solution, well, not the ultimate solution, but a strongly recommended solution, at least in CAS32A, to perform certification of multi-core platforms. Now, at this point, I want to draw attention on a few things. These are just a subset of challenges. Well, first of all, communication. We are performing a very strict intercore isolation, but at some point we need to communicate, because, for example, of the big application scenario that Greg was mentioning before. So we need to be able to transfer data among cores or between cores, and we have to do it in a way that doesn't violate the nice partitioning or the nice independence that we have between the timing of different cores. And on top of that, well, SCE works at a very low level on the hardware. It's on the OS level at the very least. So it's important to understand how we can verify SCE altogether. And to do that, we have to start from the bottom and then export the verification process, the verification properties to the whole framework. And we started at some point. We have some work in the pipeline on this. Well, in terms of optimization, as I said, we have profiling, but it's done in a very naive way at the moment, just a proof of concept of what profiling can really do. So effectively, one possibility is to refine the way we do profiling, and instead of considering a monolithic task, consider a profiling which is more based on a branching condition in your task, in your application. And finally, ideally, this is not the best model because we have SCE that is working together with an OS and manages a group of SMP cores effectively. But in order to contain the failures and contain the concern, a model like this would be more desirable, where SCE is operating at the hypervisor level, managing all the resources, and then you can deploy different OSs on each of the cores. So you have a nice separated software architecture. All right, so with this, basically, I want to a little bit review and mention one more important point. So the first one was, well, SCE is structured in a certain way as the goal of exporting this view of the architecture as a logically federated architecture on top of a commercial multi-core. And we saw a little bit the relationship between SCE and CAS32A in terms of design principles, again, not implementation level. This CAS32A is reminiscent of many points that were embedded in a draft that we produced after we were confident enough that the philosophy behind SCE can work for avionics platform, which is the minimal multi-core avionics certification guidance. This is an initiative that started somehow from Illinois and then has been endorsed now by a number of institutions around the world. And the point is, where we want to go from here? Well, we want to go to make this a standard. Where we are is at the level of guidance. So we are fairly at the beginning. So we're getting started with this. But we believe that the philosophy is solid. And what we really need now is your help. And so effectively is, we need as much, not consensus, we need as much contribution as possible. I really encourage everybody in this room, with their own institution, with their own concern, to get on board. And we can work together toward a more refined version that tries to capture the needs of different agencies as well as different industries as well as different application domains. And with this, I want to really thank you for your attention, and I'll be happy to take some questions if we have some time for it.
I guess just one question. We're really terribly from the scale. Yes.
So is this awesome software open source?
It's academically open source in the sense that we have no problem in sharing it. The only problem we have is that that's currently the latest version is implemented on P4080, and we have some NDA to share some of the components of the OS that are part of the private code base of Freescale at the time. And so if we can sort it out, we can probably at least have an agreement.
Okay, let's thank Renato.
Thank you very much.